Hey gang, welcome to another Electronics and More video. In today's video I'm going to be showing you another crank generator which I just completed. The motor that I used I picked up at a restore, also known as Goodwill store. This is a very expensive permanent magnet DC motor. The specifications are right over here. 220 volts DC, 3,500 RPM, 12 amp, 3 horsepower, and it's rated for continuous use. DC permanent magnet motors, like you see here, are very expensive. They sell between $400 and $500 each. I was able to pick this one up that you see here for only $25. I stole it. And as a result of being able to purchase it for such a low price, I decided to make this really nice, compact crank generator unit like you see here. Now, not only did I design it to be a crank generator, but I'm also going to be using it with a sprocket, which is going to be mounted right on this pulley, right in front of it. I did order that. Once the sprocket is mounted on the end of this shaft, or just on the inside, alongside the pulley, I'll then be able to have the ability to generate power by hand up to around a 40 watt maximum, around 3.25 to 3.5 amps of current. Or if it's connected up to a bicycle using this chain, and the way this frame was all designed, this will fit perfectly right behind the bike, which is on a stand. I'll be able to take the chain, put it around the sprocket, go straight ahead around the sprocket on the bike, and be able to ride the bicycle while producing a lot of power. When connected to a bicycle, I can expect between 7 and 10 amps of current coming off this permanent magnet motor. In a minute, I'm going to turn the camera and show you what the inside looks like of this motor, show you how the brushes are set up. This is not a brushless motor. It does have an armature with heavy-duty brushes, but for the amount of time that I'm going to be cranking this to produce power, it's not going to make any difference that there are brushes on this motor. The entire frame that you're looking at I designed, and it's made out of slotted angle steel. All these little holes here, I had to drill some out to mount these switches. And it's also made using flat stock steel. The bolts are all 5/16, and there's a few 1032 screws holding the accessory socket in place, as well as the bracket for this regulator. The battery is a sealed lead-acid battery that I found from an uninterruptible power supply, which was thrown away in the trash. Luckily, the battery was like brand new, so I kept that. I added this light right here, which is very, very bright. It has multiple chips on the board. It's a cob LED. This is the same one that I used on my key machine video, and they're very inexpensive, and the quality appears to be very good. I'll place a link in the video description area if you're interested in either this cob LED, there's many different types, or if you're going to be interested in this voltage regulator. This one is designed to accept up to 40 volts DC on the input, and it maintains a steady 12 volt output, or very close to it, at up to 10 amps. Switches like you see here, as well as the accessory socket, can also be found at the website. I chose the heavy gauge steel like you see here and the particular layout because it's going to be very strong when I go to rotate this pulley, and the purpose of this angle is not only to shore up this corner to keep it from moving around, but it also gives me a place to put my hand and hold while I grab this with my right hand and I go to crank the generator. On the bottom of the unit are 4 rubber feet secured to the frame. The 2 pulleys for this project, one is a 5-inch pulley and the other one in the back is a 2-inch pulley. Now the ratio is 1 revolution on the large will give you 2.6 revolutions on the small. So if I'm rotating this an average of 150 to 160 times per minute, I'm going to have a little over 400 RPM on the shaft of the DC motor. Because this is a DC motor, if you rotate it in one direction, you're going to have the positive and the negative in one place. And if you rotate it backwards like this, Now the negative and the positive are going to switch. Now if I wanted, I could have easily taken a Schottky bridge rectifier, and by doing that I could have taken the black, which is the negative, and the red is the positive, which is hard for you to see, and taken those and put those into the alternating inputs on the bridge rectifier. Then I would take the negative and positive outputs and connect it to the circuit. By doing that, I'll be able to turn backwards or forward, and the negative and positive will always be in the same place. I have a video demonstrating this, which is very good. If you're interested, you can click on the circle with the eye right over here. The drop-down menu will appear, and you can watch that video. Because I'm right-handed, it's designed this way, and the arrow right here shows direction of rotation, which is that way, so I would go this way. There was no reason for me to add the full wave bridge rectifier, and the reason why I don't like to use them if I don't have to is because you do lose a little bit of power when you use one of those full wave bridge rectifiers. The shaft of this motor is 5/8. It's keyed. This pulley here has a set screw, but it's not secured to the shaft. I use it simply for putting grease around the shaft of the pulley, so this rotates much easier. In a minute, I'll show you a close-up of how I did this. There's a plastic washer on each side, sandwiching the pulley along with 2 metal washers. In here are 2 jam nuts. I use those to get the slack taken up on the pulley on this bolt, tighten them down securely so the pulley doesn't flop around in position, and then I bolted it onto the steel angle here in a slot that I made, which is about 2 inches long, and there's a very large washer and a lock nut. This part of the handle is made from the same steel you see right here. I wanted the handle as close to the end of this pulley as possible, and you could not just drill through because you go into the belt, so I made the bracket like you see here. And this spins free as well. Better angle there. The purpose of this steel angle going across the middle is to give this battery an area to be nylon tied onto so it can't move, and it also ensures this metal frame stays nice and square. On this channel I also show other crank generators. If you're interested, be sure to click over here, circle with the eye, and you'll see the drop-down menu. Now to use this, there's a couple of different ways I can use it. Over here you see a switch that says low, high. Over here it says LED. Over here it says battery on and then off. The LED switch simply turns on that LED cob light. Now this is ideal. A setup like this is ideal if you're going camping. You would bring this if you're going to be camping out for a few days, along with a folding solar panel. So during the day you use a solar panel, and at night you have power by using the crank generator. Down here, you could choose to use power directly from the battery at this 12-volt accessory socket. The generator does not have to be moving with this handle to produce power. The good thing is, while power is coming off this battery, you can also crank the generator to charge the battery up. Now, if the battery drops way down in voltage, it's going to be harder to turn this. So what I did is I added a resistor over here. You can see it. I'll give you a close-up of that as well. And that resistor is there. It's a 3 ohm resistor, 15 watt, and it's in series with the power going into the battery. So it makes it easier to crank that battery up to charge it. And then once you get the voltage up a little higher, you could put this to the high section where it is now, and it'll be very easy to crank. So if it starts off very tough, switch it to low, get the voltage up on the battery, and then once it's up, I can switch it to high. If I decide to use this with the sprocket on a bicycle, there's no reason to touch this. I would leave it on the high position. And if I only wanted to use power coming off of this motor, going through this regulator into that socket, I would leave it in the down position. Now the battery is no longer being used. I'm going to have a regulated output coming off of this unit right here, going into the accessory socket. When it's in the up position, it's going to give me the voltage off the battery. So if it drops down to 11, I'll have 11 at the socket. If I decide to crank it up like this, the voltage will rise to 14 or 15 on that battery at the receptacle, just like in your vehicle with the engine running. So I'm going to put this back to off. Now it's going to be generator only. The good thing about this, I have this unit right back here. This power inverter can be plugged directly into this receptacle, and if I needed to power 120 volt items up to around 100 watts, I can do that using the accessory socket. Also, I have a USB port up to 2 amps, so I can plug this in right here, leave this on battery, plug in my cell phone or a tablet. Battery starts to go down in voltage, crank it right back up. Now I made this to plug into the accessory socket, and the reason why I made that is because I want to have the ability with the alligator clips to send 12 volts, regulated or unregulated, to another electronic device if I had to. The wire right here coming off the motor goes to this. All it is an unregulated output directly off the motor. It will supply up to 40 volts by hand. Right here is a Schottky Diode. It's a 15 amp and it has a very low forward voltage of 0.12 volts, which is the same for this one right here. And the reason why you want to use one like that is you want to have as little voltage drop as possible across that diode, and you want to ensure that you get the most power out of the unit. So using an ordinary diode, which has a forward voltage of 0.5 to 0.6, you're going to have more losses. So keep it as low as possible. This is a 10 amp fuse coming off of the battery. Now let's take a look at the bottom of the unit. Here you can see the rubber feet. And you can see the diagonal brace, the bolts. You can see the wiring that's going into the DC to DC converter. It says 12 volt 10 amp max output. This is riveted together on the corners. Let me show you the brushes on this unit. They're very interesting. Let me give you a close-up on that. Now to remove these brushes, it's just a spring-loaded clip. You push in. This is what the clip looks like. Spring steel. And that pushes on the brush, causing it to be pressed right up against the commutator. Let me pull this one out and show you. There's one of them. So you get the wire for the power coming off. But you notice over here, one of these brushes, the other one does not have it. There's 2 wires going in. And I've never seen that before, but I think what it is, inside this brush at a certain depth, there's a loop. And when the brush wears to a certain spot, this circuit opens up and you'll have an indicator wherever this motor was attached on a panel, letting you know that it's time to change the brushes. Let me put this back together and flip it around. On the end of the unit there was a plastic cooling fan. That's no longer needed. That was when the motor was being operated using 220 volts. Here's a better look at the mounting for the accessory socket as well as the voltage regulator. I made a bracket. It's a 90 degree. Goes all the way across. Let's take a look right inside that motor. Right over here you can see the lock nut. There's part of the oval slot that I made. It goes from there all the way to here. So this is adjustable left and right. Here's where the resistor is mounted to limit the current charging the battery. And you can see soldered connections. Here's a look at the rear side of the unit. Here's a good look at the pulley end of the unit. 1/2 inch bore in that pulley, 1/2 inch bolt, plastic washer both sides, steel washer, 5/8 bore. Got the key right there. Nice snug belt, and here's the bracket that I made, secured with the 2 Phillips screws. Washers here, larger washers on the back. In this image here, you can see the armature as well as one of the very thick magnets inside the motor. Alright, this is a very simple circuit diagram. M is the motor, got the negative and positive leaving the motor. Over here is the Schottky Diode, which has a 0.12 forward voltage. From that point, it goes down and it goes into a 3 ohm 15 watt resistor right here. The switch is in parallel with the resistor, so when the switch is open, it's going to be a lower level of power flowing into the battery. When the switch is closed, you shorted out the resistor, allowing the full flow of current. Also from that point, it goes into a double pole, double throw switch. So over here on the left, these two would be the two center pins of a double pole switch. And then you'd have this one here and that one there would be two pins on the bottom of the switch. This one here and that one there would be the two pins at the top of the switch. The way it's shown right now, the switch is in the on position, which means power is coming off of the battery, and you'll also be able to charge the battery at the same time. When the switch is in the other position, instead of going down, down, if it was slanted to there and to there, then power would go from this diode directly into the voltage regulator, and then you'd have your 12 volt regulated output coming off of the crank generator. In the other position, going back down, you're going to have whatever voltage is on the battery. It will not be regulated, but it will be between 11.5 and 15 volts. After that fuse, it goes into the switch, then it goes all the way around to the resistor connecting to the generator. Now, from here on the positive of the battery, it goes to the switch, to the LED, which is 12 volts. I did put a 15 or a 20 ohm resistor to keep it a little lower, to reduce the current a little bit, because sometimes it will go as high as 14 or 15 volts. Other side of the resistor goes to battery negative. And that is it. There's not much to it. Let me give you a couple of demonstrations. Alright, let's try out the accessory socket with the battery power. So I'm going to plug in this inverter. Alright. There's my phone. Let me just put that right over there. Should come on. Now when I put the switch to on, it, like I said, battery power only. Okay. And over here it's got the lightning bolt showing that it's charging. And if I want, I can hold it right here. And I can crank as well to produce power. And you can see it cranks very easily. It's not a lot of work going into cranking that. I could pop this out. Take this 75 watt light, which is 120 volts. Plug that right in. And we'll turn it on. There you go. Shut it down. Okay, now I'm going to show you powering up the phone using the generator only. The battery is off. All power is coming off of this motor directly into that unit to power the phone. Now it's extremely easy to charge USB devices up to 2.5 amps because that's only around 10 to 12 watts of power output, and there's not going to be too much resistance on this pulley while cranking. Here we go. You'll see it come on in a minute. There you go. That's as fast as I have to go right now. See, the phone is on. It's very slow. And I am getting a good output on this. And I can hear the fan going on here. And then I can stop and it'll turn off. No more charging. And the fan is off over here. Now, unless a load is extremely light at 120 volts, maybe 20, 25 watts or 30, you would not want to be cranking this and have the generator supply the power to that unit without having the battery connected in parallel. It's much easier to have this connected to that unit, and then as it's on, you could push this to the low position, and then you could rotate the crank and charge up the battery while the inverter is running. Every 10 watts of power output at 120 volts is going to be drawing around 1 amp at 12 volts DC. And I could put out around 3.5 amps, so that would only give me around 30-35 watts of output for a 120 volt device. So ideally, battery must be connected. If I had a sprocket connected to the shaft of this motor and it was connected up to a bike, then I would have no problem powering this inverter directly off this motor because there'd be enough power supplied to the inverter. Now the next thing I want to do is take this output and I'm going to connect it up to this 45 watt, 90 watt quartz halogen headlamp. I think it's an H4, and you're going to see how easily I could power this up on the 45 watt setting. So let me hook this up. I'll also have the digital multimeter connected so you can see the voltage is around 12 volts. After I do that, I'm then going to show you how much current is being supplied to this lamp. I'm going to hold it right here, and I'm going to crank. Watch the voltage, watch the lamp. And you can see it was all the way up to 13 volts, and I didn't have to get carried away cranking. Okay, we're now going to be measuring DC current. The voltage that we hit was around 13.13 just a minute ago when I checked this lamp. So now we're going to see what kind of current I can get to flow through that lamp. As you just saw on the meter, we were averaging around 3 amps of current. We did hit a peak of around 3.17. If you multiply 3 amps by around 13.2 volts, you'll end up with right around 40 watts, which is exactly what I said the output is for this unit when cranking by hand. When the motor shaft is connected to a bicycle, I can easily expect more than double that amount. I hope you enjoyed this video. If you did, be sure to rate it a thumbs up, subscribe, and post links to this video on other websites and blogs. Also be sure to check out my video playlist as well. Thank you very much for watching.